Hey folks, how's it going? So last night I was just cruising TikTok a little bit, happened to come across Rakia's live. He's a flat earther, and they're going on, and he had Gean Techman on there, who's a narcissistic, freaking egotistical jerk, and he's been called up many times. Now he thinks he's quite clever, and the more you watch him and look up all his crap he says, the more you realize he's just a dumbass, like all flat earthers. And he happened to bring up this thing called the Vacuum Catastrophe. He thinks somehow this disproves the globe model and heliocentric model. That was funny because, honestly, fully disclosure, I didn't know what this was. I never heard of this, so I looked it up. And Gean Techman needs to look it up too, because what he cites is completely wrong. Right now, comes down to it. He thinks if he had a teacup size of a vacuum, like of space, which is a nearly perfect vacuum, but not a perfect vacuum, it would cause all the oceans on the planet to boil instantly, like just go straight from liquid water straight to a gas, no questions asked. Right. But we have freaking vacuum chambers on our planet, and you can literally, what would happen if you open a vacuum chamber bigger than a cup of tea? And what would happen if you open up the vacuum chamber instantly in our atmosphere? Okay, I'm gonna tell you what's going to happen. All the air is rushed inside. That would be it. It wouldn't boil a single freaking thing. He's talking so much crap. It is hilarious. But let's watch this live. And then, for those who don't know it, I did a little AI thing here because it kind of helps explain it a lot better than me trying to get it all out. So I'm just going to learn about it. But yeah. So have watch this. This is great. This is flerf logic at its best.
My question is just, what is a teacup of space? That's all.
Wait, are you crying? Holy space! Did you come up to cry?
Is this decorum?
Ask a genuine question.
What's a teacup of tea? What's a teacup of orange juice?
A teacup
What's
of
a teacup
tea
of
is
gasoline?
tea. A teacup of orange juice is
so
orange
a teacup
juice.
size, right? It's a reference of size. Okay. So one teacup of your ideal of space
is
that has the vacuum value of 10 to the negative 17 torr. If, say, we were to encapsulate that amount of space, right, void of particles, and we brought it to our world full of particles, it would make all of the oceans boil.
So why don't you?
Why? Do you know why? Do you know why it would make all the oceans boil? What happens? What happens when you put a cup of water in a vacuum? It boils.
But what happens when you put a vacuum inside of a pool?
You see what I mean? I mean, Gean Techman thinks because if you put a cup of tea, now it has to be a warm cup of tea, it can't be cold, right? It has to be have some sort of energy in it, so it has to have, even if it's kind of sort of warm, then it's got heat energy, and then because of that, when you remove the air, then those molecules in there, the heat is able to expand more, and then it will actually it will kind of boil. Now it's like the same if you have a syringe, put warm water in it, put your finger against it, seal it up, pull the syringe out, which causes a vacuum, and create a vacuum chamber with a syringe and your finger, and the water will start to have bubbles in it, right? Like if it's boiling. Okay, and I grew up in Alberta, Canada. Went up to the mountains quite a bit, and you would notice, like I said, water boil up quicker over the fire when you're trying to boil some water, because at higher altitude, right? So that's what he's talking. Because he thinks a cup of tea inside a vacuum chamber, so you have a vacuum chamber and you remove all the air out of it and bring the pressure right down low, and a cup of tea inside this. Now it's encapsulated, encased in, because obviously you have atmosphere outside, so it's going to push in. The cup of tea will boil. So he thinks if you take that vacuum, that low pressure, the extreme low pressure, nearly nothing, and put it inside a massive air system with loads of pressure and molecules and stuff like that, then it'll cause all the matter around, all the water outside of that in a tiny little vacuum to boil instantly. So Gean doesn't understand how vacuums work or what a vacuum is. I mean, all in all, technically, air molecules in between the molecules of the air is a vacuum. Because what's a vacuum? A vacuum is an absence of matter, an absence of anything like that. So in between the molecules of our air, there's nothing, right? Because there's space between. Technically, it's a vacuum, right? That's why we have 14.7 psi at sea level. You go up higher, less molecules, less pressure, more space between them, right? So bigger vacuum, go up higher, 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 till eventually the vacuum space gets larger and larger and larger, and then you get into like less and less pressure, right? And they understand this. Now, honestly, if we had a container, then, and they say you have to have air pressure, the pressure would actually equalize all the way up to the firmament, that the magical dome that the claim is there, but nobody's ever seen it, touched it, or felt it, or experienced it, or anything like that. But yeah. But then the pressure would not be higher, because they say you need pressure to push off of. So then if you go up closer to higher up, wouldn't the pressure increase? But it doesn't, it decreases. See, so their logic is fallacious right from the beginning. But yeah, so if you have a vacuum, tiny little vacuum inside a massive air pressurized system, what's going to happen? Well, then you open that up, all the pressure is going to move into that vacuum. But when you have a teacup which has a pressure inside the water, like say warm water, warm tea, whatever, inside a vacuum chamber, then when you move the air, then it's a higher pressure inside that, it's going to move out, and that's going to cause the water to boil. Because it doesn't have the air pressure, the atmospheric pressure pushing in, stopping it from the molecules expanding out. But Gean doesn't understand this. This is simple freaking like grade 6 freaking like science stuff. I mean, it's not that hard. But yeah, let's continue on.
So you put a cup of your space and an earth. It's a full contradiction, my guy.
He
full
said
contradiction.
Inside of a pool, guys.
Inside of a pool?
Yeah.
The pool would disappear.
Wait.
Oh, what a dumbass. No, okay, if you put the vacuum, a teacup of vacuum, in a pool, what would happen is as soon as you open up, let's say you're holding a vacuum, so you open it up, the water move into the pool. Let's say it just goes, it'd be like a drain, open a drain up, and it pulls in. That's how water goes into a drain. Is that less pressure, lower pressure into the drain. Water is higher pressure, fills and goes into the drain. So what happens if you open that tea into let's say a swimming pool full of water, the water goes into the teacup. It just goes, and the teacup be full of water. But Gean's a stupid ass. He's just stupid. I mean, all of them are dumb. They believe his bullshit. I think, is he lying? I think he's lying. You can't be serious, Gean. Can't be serious. You don't believe this, do you?
Wait, you couldn't do it because isn't a vacuum a devoid of matter and water is
the flat Earth, yo. Look, you see what he just said? Vacuum inside of the pool. What?
It would be a devoid of matter. Hold on, let's see. Let's make sure we heard him right. Hey, did you say a vacuum inside of a pool?
Am I allowed to speak? Am I allowed to speak?
Did you say a vacuum inside of a pool?
What? Yeah, I did say that.
Wait, isn't a vacuum a devoid of matter? That's the definition I know it by. Do you know it by a different definition?
If I was allowed to talk, I would be able to tell you what I'm talking about.
Well, you seem to be talking to me just fine. Do you want me to hold your hand?
So what I'm talking about is if you took a vacuum chamber and put it into a body of water and then opened it, would the body of water boil? Because that's what you're talking about. That's what you're saying.
Hold on, wait a second. How could you do that? Because once you open the vacuum chamber, it's no longer a vacuum chamber. Does that container have to be sealed in order?
That's my point. How do you bring a teacup of space down to Earth? That's the whole point of what I'm saying. What's a teacup of space?
What is
Hold on.
space?
Only classics. How do you have gas pressure on Earth without a barrier?
I thought we were talking about your special
all pressure
problem.
gradients. All pressure gradients demand a physical barrier, with the exception of the globe and the globe only. It's a scientific outlier that you're defending, but it can't physically be demonstrated. You can't take a basketball to your hardware store and say, "Hey, Jimmy, go ahead and put some propane on the outside of this basketball for me." Your whole ideal can't be demonstrated. So before we get into this ideal of teacup of space and in a pool, bro, the Earth has a full-blown problem. We have an open sky above us. Gas pressure would seek equilibrium. I've used this metaphor over and over again, but that ideal is like thinking of dropping a drop of blood in the ocean and expecting it not to mix.
You're the one that said the thing about the...
We have a force called gravity. It holds all matter to the earth because gravity is real. I've asked this just before all this. Actually, I muted because I was in there and I asked them to explain the Pound-Rebka experiment. And so far, my track record is not a single flat earther has ever been able to reconcile the Pound-Rebka experiment without invoking gravity. It's just they normally run away, and in this live here, I asked, didn't see anything horrible. I asked them to reconcile it, and they muted me for a while. And just before this, I was able to start commenting again. That's why I started recording actually, because I wanted to see if they're going to mute me again as soon as I asked what the Pound-Rebka experiment. But I think one of the flat earthers, Luke Flatwalker, you're man-child, aren't you? Because all I do is ask about that, and you just mute me and run away. It's my cat.
About the teacup of space.
Right. I'm the one that's quoting the vacuum catastrophe that you're too lazy to look into.
Never heard of it.
What else
honestly.
do you need?
Never heard of it, honestly.
Right. I know you haven't. I know. Look into it.
I told you that talking about it.
I told you that the first 15 seconds when you started talking. I said, have you looked into it? I know you have.
Hey, Gean.
So look into it.
Hey, Gean, for the other 107 people in the room, Gean, why don't you just lay it out real simply and quickly, short summary of what it is for everybody.
The vacuum catastrophe is a misalignment of what they call quantum mechanics meets observation. And so, and as I was simply just trying to explain, it's off by an error of 10 to the 120th power. It's considered the biggest error in all of physics. And what I was simply highlighting is one of my highlights of the mention of the vacuum catastrophe. I didn't make this up. That, again, vacuum energy, space, in contrast, us here on Earth, that vacuum that's around us, this big old vacuum, big old massive vacuum of space around us, one little tiny little amount of space to the equivalent of a teacup. If we were to, and this isn't possible because this isn't a real thing, but if we were to take this teacup of vacuum energy and then bring it down here on Earth and say it was a little cup and we opened it up, right? That vacuum would be enough to make all of the oceans boil.
That is not what the vacuum catastrophe is. See, Gean doesn't even know what it is. It's a discrepancy between the theoretical math and what is predicted by quantum mechanics and what is actually observed in cosmology. I'll explain it here later when I play a little thing from the AI. Explains it a bit more in detail, and also you can read it as well. But yeah, that's nothing to do with what Gean's saying is bullshit. See, he started off with kind of like I did. He goes and then reverse left, and this takes off, and he goes to top left. That's where Gean belongs. Dunning-Kruger. That's what Gean's guilty of. He's Dunning-Kruger.
So again, a full-blown problem, not for the globe or the flat Earth model, but directly the globe heliocentric model that has no barrier around it, but it holds gas pressure with a magical pseudo force called gravity and the bending and warping of space-time. Come on, guys, time to grow up.
Okay, so because I had heard of the vacuum catastrophe and looked into it a bit, I decided that what I was going to do, just kind of make it easier to get everything explained and have it printed on the screen, is I went and asked Gemini, which is an AI that is used by Google and several other things. And it does base and gives all the sources at the bottom. After the statement, it gives the sources. You can click on the sources and see where it got this information from. So it draws in several different sources. And they're most like, normally, actually, 99.99% of the time, they are credible sources that you can look at and fact check the AI. This is something that flat earthers don't always do, and they ask certain questions with ChatGPT. They try to twist it and make it answer what they want it to answer, because that's what ChatGPT does. It gives you the answers it thinks it wants you to hear. So here we are. I'm gonna ask the questions here. You can see the questions I asked because I left it printed on there, and then you can see the response, and I've let it so that it plays so you can hear the AI voice. So let's get started on this, and let's completely destroy and debunk everything Gean Techman said. And I've already kind of done that, but it's just going to back up everything I said, where I'm going to show facts and evidence and citations. Something Gean's never done.
The vacuum catastrophe refers to a significant discrepancy between theoretical predictions and observed values concerning the energy density of the vacuum of space. Here's a breakdown. Vacuum energy. In quantum field theory, even seemingly empty space, a vacuum, is not truly empty. It's filled with fluctuating quantum fields, which contribute to a baseline energy known as vacuum energy. Theoretical calculations of this vacuum energy density, based on quantum field theory, yield extremely large values. Cosmological constant. In cosmology, the cosmological constant is a term in Einstein's field equations of general relativity that represents the energy density of space itself. It influences the expansion of the universe. Observations of the universe's expansion indicate that the cosmological constant, and thus the vacuum energy density, is very small. The discrepancy. The vacuum catastrophe arises from the immense difference between the theoretically predicted vacuum energy density and the observed cosmological constant. The theoretical value is vastly larger, by as much as 120 orders of magnitude, than the observed value. This huge mismatch is what's referred to as the vacuum catastrophe. Significance. This discrepancy is a major unsolved problem in physics, highlighting a fundamental gap in our understanding of quantum field theory and cosmology. It shows that there is a large disconnect between what quantum mechanics predicts about the vacuum of space and what general relativity and cosmological observations tell us about it. In essence, it's a profound puzzle about why the vacuum of space has so little energy when theory suggests it should have a tremendous amount. It's important to clarify that the vacuum catastrophe is a problem within the realms of quantum field theory and cosmology, and it is not directly a problem for the heliocentric model. Here's a breakdown. Heliocentric model. The heliocentric model describes the arrangement of our solar system, with the sun at the center. This model is well established and supported by a vast amount of observational evidence. Vacuum catastrophe. This is a problem concerning the discrepancy between the theoretical and observed values of the energy density of the vacuum of space. It's a fundamental issue in theoretical physics, particularly in the intersection of quantum mechanics and general relativity. Relationship. These two concepts exist in different domains of physics. The heliocentric model is about the structure of our solar system, while the vacuum catastrophe is about the fundamental properties of space itself. While both relate to our understanding of the universe, they are not directly interdependent. The vacuum catastrophe is a problem that exists within the current understanding of how the universe works on a very fundamental level. It is a problem that exists within the current cosmological models that are used in conjunction with the heliocentric model. In essence, the heliocentric model is a description of our solar system's structure. The vacuum catastrophe is a problem with our understanding of the energy of empty space. Therefore, the vacuum catastrophe does not pose a direct problem for the validity of the heliocentric model. Quantum field theory, QFT, is a theoretical framework in physics that combines quantum mechanics with special relativity to describe the behavior of subatomic particles and their interactions. Here's a breakdown of its key aspects. Fields as fundamental. Instead of viewing particles as discrete objects, QFT treats them as excitations of underlying quantum fields. For example, an electron is seen as an excitation of the electron fields. These fields permeate all of space, and their fluctuations give rise to the particles we observe. Quantum mechanics and relativity. QFT merges the principles of quantum mechanics, which govern the behavior of particles at very small scales, with the principles of special relativity, which describe the relationship between space and time. This combination is essential for understanding high-energy phenomena, such as those occurring in particle accelerators. Particle interactions. QFT provides a framework for describing how particles interact with each other through the exchange of force-carrying particles. For example, the electromagnetic force is mediated by the exchange of photons. Applications. QFT is the foundation of the standard model of particle physics, which describes the fundamental particles and forces of nature. It also has applications in other areas of physics, such as condensed matter physics, where it is used to describe the behavior of quasi-particles in materials. Key concepts. Quantum fields. These are the fundamental entities in QFT, and their excitations correspond to particles. Virtual particles. These are temporary fluctuations in quantum fields that mediate interactions between particles. Renormalization. This is a technique used to eliminate infinities that arise in calculations in QFT. In essence, QFT provides a powerful and comprehensive framework for understanding the fundamental constituents of the universe and their interactions. It's crucial to understand that the vacuum catastrophe is a problem within theoretical physics, not a direct challenge to the established understanding of Earth's shape or atmosphere. Here's how to clarify the connection. Vacuum catastrophe and fundamental physics. The vacuum catastrophe is a conflict between predictions from quantum field theory and observations of the universe's expansion related to the cosmological constant. It's a problem at the most fundamental level of how we understand physics. It concerns the energy density of empty space, Earth's globe and atmosphere. The Earth's spherical shape and the existence of its atmosphere are well supported by a vast body of observational evidence from many fields, including satellite imagery, observations from aircraft and ships, the behavior of gravity, and many other scientific observations. The atmosphere is held to the Earth by gravity. The pressure gradients within the atmosphere are a result of this gravitational pull. Lack of direct connection. The vacuum catastrophe does not directly invalidate the scientific evidence supporting a spherical Earth with an atmosphere. The vacuum catastrophe is a problem that physicists are trying to solve within the framework of our current understanding of the universe. It does not mean that all of our understandings of physics are wrong. It points to a gap in our current understandings. It is important to understand that the vacuum catastrophe is a problem that affects cosmological models. Those models are used in conjunction with the knowledge that the Earth is a globe with an atmosphere. In essence, while the vacuum catastrophe is a significant puzzle in physics, it doesn't create a logical conflict with the well-established scientific understanding of Earth's shape and atmosphere. The concept of a teacup of space is a bit tricky, as space itself is a vacuum, meaning it's the absence of matter. However, we can interpret this in a couple of ways and address the potential effects. Understanding the challenges. Vacuum versus matter. A perfect vacuum contains virtually no particles. So, a teacup of vacuum wouldn't contain significant heat energy to transfer. If the teacup contained some form of extremely cold matter from space, the effects would depend on the nature and amount of that matter. Heat transfer. For something to boil the oceans, it would need to transfer a massive amount of heat energy. Possible scenarios and effects. A perfect vacuum. If it were truly a perfect vacuum, the primary effect would be a localized, extremely rapid expansion as the vacuum tries to equalize with the surrounding atmosphere. This could cause some localized flash boiling of water, but it wouldn't be anywhere near enough to boil the oceans. Extremely cold matter. If the teacup contained extremely cold matter, like frozen gases, it would initially cause localized freezing. However, the Earth's oceans contain so much thermal energy that the cold would quickly dissipate. It is important to remember that the ocean is a massive heat sink. So for any significant change in temperature, an extreme amount of energy would have to be transferred. The scale of the oceans. The oceans are incredibly vast. To raise the temperature of the oceans enough to cause boiling would require an almost unimaginable amount of energy. In conclusion, a teacup of space, a vacuum, wouldn't have the energy to boil the oceans. Even extremely cold matter would have a negligible effect on the overall temperature of the oceans. Therefore, the answer is no. A teacup of space brought down to the surface of the Earth would not make the oceans boil instantly.
So there you have it. As you can see there, and even AI agrees with me, everything that Gean Techman was saying was a load of crap. Even at the end where I included on, would a teacup of space, i.e. vacuum, brought down to the surface of Earth, would it cause the oceans to instantly boil? And that answer is, as I expected, and I already said, no. Because you need a great, vast majority amount of heat to cause the oceans to boil. As I said, all that water is a massive heat sink, and it wouldn't boil. All it would do is, like, as it's said there, the AI is locally, and it's talking very locally, as in, like, teacup size. The vacuum is that as it's that water is moving into the vacuum, being that if it's a perfect vacuum, it would cause probably very localized boiling of the water, and the amount of energy it takes to move into that teacup, so be probably the teacup size, would cause maybe some of the water to boil. Being that if the water is at a temperature, it could. If the water was extremely cold, like just slightly above freezing solid, then would there be enough energy and heat energy to transfer into it to cause it to boil, or would it cause it just to heat up? That's that's just here nor there, ideally. But would a teacup of space, cause the oceans of the whole entire planet to boil? Absolutely fucking not. Not even in the slightest. And even as AI said, if you had something like super cold, like friggin' purified ice hydrogen and brought down, would it freeze the oceans? No, it would not. It would probably freeze some liquid, maybe water around it to a point, but then that cold would quickly dissipate, and you'd go from a smaller teacup of ice to a slightly bigger probably ball of ice, and then that would be it until it thawed out again from the heat of the oceans. So that's about it. Gean Techman talking shit again, misrepresenting something, and probably because he read a headline and then made an assertion while having a blind bit of idea what he's talking about. Thanks for watching. Don't forget to follow me for more videos. Click the like, comment, and also head on over to my YouTube channel, Curious UK Debunks. That's Curious UK Debunks. I go live on Sundays and Wednesday evenings UK time, unless there's things happen. I do have family, and sometimes family stuff comes up, and I'm always able to make it on, but I do try to make it as much as I can. Thanks for watching, and I will see you again. See ya.